let's just go to our actual instruction. We have taken values for R2 and R1 as 3 and 1 respectively. Let us load those values now. Okay. So this first instruction, what it is supposed to do is R2 value is supposed to be left shifted by 2-bit position, and that content should be added with R1 and the result should be stored in R0. Okay, let's see what exactly is R2 value. R2 value is nothing but 3. R2 is nothing but 3. Now on this R2, logical shift left is to be performed. Logical shift left means you have to move in this particular direction by 2 times. Okay, so after the first shift, what will be the value of R2? It will be nothing but 110, which is nothing but 6, because we are performing 3 into 2 since it is logical shift left. And the second time, what will happen to the value of R2? It will be nothing but 12, because it is similar to performing 3 into 2 into 2. Okay, so in this particular situation, we got that R2 value is actually 12. Now this value 12, okay, I'm writing 12 in, actually it is in decimal. Okay, this should be added with R1 content. What is R1? R1 value is 1. Okay, so what's the result? 13. It is 13 in decimal. What is the value in hexadecimal? D. Let's see if the value D is stored in the register R0. Okay. Yes, so we got the answer D stored in R0. In this particular instruction, we have just taken a new value for R1 as 12 because we wanted to show the same example that we discussed in theory. What happens here is R1 is left shifted by 1 time and the result of that is stored in R0. Because R1 is 12, left shift by 1, we know multiplies it by 2, so the answer for this should be 12 into 2, which is 24. Let's see if that answer is stored in R0. Yes, okay, this is hexadecimal 24. Now what we are seeing is nothing but the content of R1, the original content only, that is 12, is now multiplied by 4 times, because here logical shift left by 2 times or 2-bit position is done, which is equivalent to perform 12 into 2 into 2, which is nothing but 48. So this answer should be stored in R0. One more thing we notice is here we have used move s, so we are setting the conditional flags, okay, based on the result. Okay, let's see what happens here. As soon as we execute the next step, we know 48, which is the expected value, is now stored in R0. Because of the usage of S, the conditional flags are updated based on this particular result. Next to that, we have taken a new value 80, okay, into register R1, okay, and what we want to perform is LSR. From the theory part, we already know every LSR operation will actually perform divide by 2. Okay, so in this particular case, what should be the answer? 80 by 2 is actually 40. So answer 40 should be stored in R0. Let's see if that is the case or not. Yes, and in the second case, that is this particular case of LSR hash 2, what should happen? 80 divided by 2 divided by 2, which is nothing but 20. Okay, because for every logical shift right, we are going to divide by 2. So LSR hash 2 means we have to perform logical shift right by 2-bit position, means it will be divided by 4, and this is the answer. Let's see if that is what we obtain here. Yes, and next we have LSR hash 3. LSR hash 3 means it is 80 divided by 2 divided by 2 again divided by 2, that is divided by 8 actually, and the answer is 10. Okay, let's see if that happens, and we have even used a yes here to set the conditional flags. Okay, next what we have is arithmetic shift right operation, and we have taken a value 8 and all zeros here. In binary, 8 is nothing but 1 and all zeros. Okay, and remaining bits are anyway 0. okay, but this will make sure MSB bit is actually set as 1. Okay, if MSB is 1, vacant positions created in ASR will be replicated with the value of 1. Let's see that happening. Okay, now we have taken our first value here, okay, 8 and all zeros. After arithmetic shift right, what should happen? Once when you shift to right, all bits are shifted to right, but MSB is repeated in the vacant position. So what is the answer you should get? This was already done in the theory, so I'll just write the answer. First value will be nothing but C, and all other values will be 0. Let's see if this is the answer you get. Yes. Okay, now if you perform again arithmetic shift right here, then what will happen? One more 1 will be added and all this bit will remain same. So what is this? This is nothing but E. Let's see if that is the case. Yes. Okay, next what we have is, for the same operation we have just used a different value whose MSB bit is actually 0. We have done it so that we show that in this particular case the vacant positions are filled with 0. Let's see that happening. Okay, our value is all zeros, last value is F and 0. This is our initial value, all this bit will be 0. Okay, so only thing that will be happening here is this will be shifted right, exactly similar to logical shift right. Okay, so in the first case it will be 1 1 1 1 and something like this, which is 7 8, and in the second case it will be nothing but 1 1 1 1 0 0, which is 3 and C. Let's see that happening. Okay, 78 and 3C. Okay, and have used yes here. As per the result of this particular operation, output or the CPSR content is updated. Okay, next what we have is a rotate right operation. Let's see that happening. So our value here is nothing but 96. Okay, so this, when it is rotated right once, what should be the answer? And all remaining bits, let's assume that is the 31st bit, this is the 0th bit. Okay, we have to wrap it like this. Okay, so what will be the initial value? Because 0 is shifted, there is no problem, MSB will still be 0, and here you will get some answer like this. So what is this? This is nothing but B, this is nothing but 4. Okay, and because of which 4B is the answer you will see in R0. Okay, and in the next case, when you rotate this once again, what will happen? This will come to first position, all zeros. Okay, and in the last position what will happen? 1 0 1 0. Okay, and it is 0 1 0 0, which will be 8, all zeros. Okay, let's see if that is the answer you get here. Correct. On this, when you perform rotation again, what will happen? Okay, you'll get 1 1 0 0 here, and in this position it is 0 1 0 0, and here it is 1 and all zeros. Okay, which is nothing but C 1 2 3. So this is the answer you should get. Let's see if that's happening. Yes. Okay, and along with that, because we have used yes, based on the result, the conditional flags are updated. Let's go ahead with the next part. In the theory, we assumed carry to be 0. Okay, and here actually carry is 1, so I'll make some minor modification to set the carry as 0. We'll see that later. First of all, we are changing R1 as 3 so that we can take the same example as we took in the theory. Then we are comparing R1 with 4. We know R1 is 3, and when compared with 4, internally subtraction happens, which requires a borrow. So carry, because of this instruction, will be set as 0. Okay, that is the reason we simply took compare instruction here, because we wanted to modify the carry and conditional flags. Okay, so that we have same example as we have taken in the theory. Okay, so here what we are doing is we want to perform rotate right extended, okay, on arg1 and show the result in arg0. Let's see if that happens. Yes, so 1 is the exact answer that we expected and carry is supposed to be 1. Okay, how did we get that? Because our value there was 3 and all zeros was in our R1. Okay, our carry was set as 0 and this particular rotation will cause 0 to come into MSB. This entire thing will shift to right side. This will be 1 and the LSB bit here shifted to carry and carry was set as 1. Okay, so the answer in R0 will be nothing but 1 and carry will also be 1. Now let us see some more examples which we didn't discuss. Okay, so here R1 value I'm taking as 2 and R2 as 3. This I have included some more instruction to show that you can use this shift with many other data processing instructions other than just move and add. Okay, instructions like add with carry, subtract with carry, compare, all these update the carry flag which belongs to the CPSR based on arithmetic carry or borrow result and not from the shifted out bit. But in case of logical or bitwise operations like AND, OR, XOR, move, test, TEQ, that is test equivalence, okay, carry flag is updated based on the bit shifted out. Let's start with the very first one, which is subtraction. We are performing logical shift right on the content of R2. Okay, then R1 minus this processed value of R2 is carried out and the result is stored in R0. What is R2? R2 in our case is 3. Okay, we are performing logical shift right by one position. Okay, this is the initial value of R2. When you perform shift right, what will happen? The entire bit content is actually shifted towards right side. So one of this bit is shifted out and the answer you get is, okay, so answer here is 1 after logical shift right of R2 by one position. Now to this value, okay, I have to perform subtraction between R1 minus this particular value. What is R1? R1 is 2. And what is this value? This is nothing but 1. 2 minus 1 is nothing but 1. So the value 1 should be stored in R0. Let's see if that happens. Okay. So next we have XOR operation such a way that R2 value is rotated right once and then that content is XORed with R1. Let's see what happens then. Okay. First of all, what exactly is our R2 value? See, in this step we have not modified R1 or R2, only R0 is updated. Okay, so same value of R2 that we took previously, that is nothing but 3. Okay, they want to rotate right by 1. What is rotate right? This content is rotated in this way that this particular value which is in LSB moves to MSB. Okay, then what will happen? So this one, if it comes to MSB position, so what exactly will be this answer? Yes, this will be the answer you get after one particular rotation. So this content should now be XORed. Okay. Now we have to perform XOR operation on this. We already know in case of XOR operation, complementary values when you see output will be 1. Are these complementary? Yes. And what about this? It will be 0. What about this part? This will be 0, 0. Okay. 0 and 1 will be 1. 1 and 0 will be 1. So this is nothing but 8. All zeros and this will be nothing but 3. Let's see if that's the answer or not. Yes, 8 all zeros and 3. Okay. Next what we have is we are performing, this is a simple operation, okay, that we have already done. arg1 content arithmetic shift right by one position and storing in arg0. What is arg1? Arg1 is 2. What is important is MSB. We already know answer is 0. If MSB is 0, this will perform exactly same as your logical shift operation. Okay, shift content to right and fill the vacant position with 0. Now this should be shifted once, so the answer is 1 here, and all this will be 0. Okay, so what is this value in hexadecimal? 1. So let's see if that's the answer we get. arg0 should be equal to 1. Okay, we got that answer. Next, we are using shift operation with comparison instructions. Let's see how it works. On arg1, we perform logical shift left by one position. arg1 is 2. If you perform logical shift left by 1, we already know that that value will be multiplied by 2. So the answer will be 4. So you're comparing 4 and arg0. What is arg0? 1. This is what is actually happening. So if it's 1 and 4, internally subtraction will happen, because of which borrow is required. Okay, so carry will be equal to 0. Okay, and because they are not equal, z will be equal to 0. And because here the first value is smaller than the second value, n value will be equal to 1. Okay, but overflow will be equal to 0. Let's see if that is what we get. Okay, n is 1, z is 0, c is 0, v is 0. Okay, and because it's just comparison, result won't be updated. Next, what we have is TST. TST internally performs AND operation. Okay, so first of all, let's see what's happening here. arg1 content, what is arg1? arg1 is 2. You're performing logical shift right 2 times. 2 by 4 is 0.5, but you know it stores only the integer, not fractional part. That is one way to say that answer which we get after arg1 logical shift right 2 times is 0. Or second option is manually write what exactly is arg1. arg1 is 1 0 and all zeros. Once when you perform shift right, you will get answer as 1. Again when you perform shift right, you will get the answer as 0. Okay, so overall the answer for this part will be 0. Now this should be ANDed with arg0 content, that is 1. And what's the answer for 1 and 0? It is nothing but 0. So the result is actually 0, which is discarded, but according to this we are updating the flags. So z will be set as 1, carry is 1, since last bit shifted out is 1.